All right, thanks, Vicki. Good afternoon, everyone. I'm very excited to be here with you. I see we have a nice group today, and I'll just say off the get-go that if there's any questions throughout the talk, please don't hesitate to ask. If anything, I'd like to do my best to address the topics that are of interest to you or questions you may have, concerns about a slide or something I'm presenting on. So the title of the presentation today, Mechanical Integrity Inspections of Ammonia Refrigeration, is appropriate, and particularly I'm going to emphasize today recognized and generally accepted good engineering practice and some of the newer technologies that are being used, ultrasonic thickness testing, vibration analysis, and things like that are pretty important in our industry. I understand there was a talk on Monday done by, I think, Michael Schreck and Miguel Sanchez about mechanical integrity as well. More on the, I think it was called Wall of Shame or something. I hope maybe some of you got to attend that. This will be a little different than that. Hopefully I won't try to just repeat what they said, where they were pointing out like practical common deficiencies and things like that. I'll try to present maybe some different material. Oh, before I get started too, just a little on me. So I'm from California, based in the Central Valley, kind of in between Fresno and Bakersfield. So my background is primarily with like the agricultural ammonia refrigeration warehouses, kind of up and down the San Joaquin Valley. As Vicki said, mechanical engineer. So that's kind of my background with refrigeration. Okay. So I was going to pose a question to start the talk today, which was why are there so many safety and environmental regulations? From a consulting standpoint, as a consultant, there's often the impression from private industry like, oh, the government is just overbearing, and there's just too much of this and too much of that, and they're always changing, and there's no consistency, and these are just kind of the common, maybe the common perception, or maybe not the common, but a perception that's out there. And before addressing that, I just wanted to go back in time a little bit, because I think I can answer that to some extent, and probably preaching to the choir to a group of mostly regulators. But I think what you guys do in doing your inspections and so forth can be really valuable to the public at large. So most of you in this room probably remember, or at least have heard of, the Bhopal, India incident from 1984. Historically, it's probably the most well-known process safety accident in the history of the world. Really tragic incident. I'll just talk briefly about it, getting to the point of answering my question. A little background on Bhopal. A company called Union Carbide had built the plant in the 1960s to produce a dangerous chemical. You can read it up there. And in 1984, in December of 84, there was an accident. And that accident led to a large chemical release of a chemical pesticide that killed many people. You can kind of see some of the stats here, absolutely devastating. Thousands died immediately. Thousands died in the next few weeks. Really, there's only estimates as to the catastrophic nature, how many people were affected. Interestingly enough, in my Popular Science magazine a couple years ago, there was even a full-page picture. You could see a big problem there, right? 6 fingers. And the hypothesis of the article was that it was a chemical accident. Whoops. It was the result of Bhopal, the accident of 84, that India still has an increased number of birth abnormalities compared to the rest of the world. Okay, that's not necessarily proven or for sure, but that's what the article was saying. And the point being that these chemical accidents can have lingering effects for long periods of time. So. And so why does this matter about a mechanical integrity talk for ammonia refrigeration? You might be, are you in the right talk right now? And my point is, the cause from the Bhopal accident, while maybe it's not 100% certain, is traceable. There's reports. So the employees of the Bhopal facility said that the accident occurred when workers who were cleaning out a clogged pipe about 400 feet from the tank caused a problem. Union Carbide, the employer, on the other hand, I don't know why that's shifting on itself. Union Carbide, on the other hand, said that water was introduced directly into the tank. So the release happened when water went into a tank, and there's like a differing perspective from the employees versus from management as to what caused the leak. Okay. Then the government did a study as well, determining that the storage of the chemicals inside the tank was beyond recommended levels. We might start thinking operating limits, consequence of deviation, right? So they were filling a tank beyond those levels. Poor maintenance practices, mechanical integrity, failure of the safety systems due to poor maintenance. One of the big tragedies when I was in college, in my engineering classes, I had to do an engineering ethics class. And one of the studies I had to do was on the Bhopal, India event. And one of the tragedies of Bhopal was that they had this comprehensive engineered safety system to prevent what occurred from occurring. But on the day that the accident happened, that the tank was overfilled or water entered the tank, it didn't work. One of the reasons it didn't work was because those functions had never been tested throughout the life of that chemical process. So another one here, the last one here, safety systems had been switched off to save energy. So they had just turned them off because the safety systems that were in place consumed energy. So all this happened prior to process safety management, prior to risk management, prior to regulations such as CalARP. Okay, but you can see a lot of the principles of the things that you enforce, particularly in the arena of mechanical integrity, testing and inspections, operating limits, and the consequence of deviation. You can see them even built into this accident to some extent. So other factors, Union Carbide had made large attempts to reduce expenses. So they were struggling financially and had made large attempts to, including cutting back on personnel. There were examples of leaking pipes that they knew of that they hadn't replaced. Some of the employees did not speak English, but yet only had access to manuals in English. That's really near and dear to the demographics of where I am. And the MIC tank alarms had not been working for several years. Okay? So, these are just a few more. I don't think I'll go over this, but there was several operators that indicated that the pressure gauge or parts of the equipment had been malfunctioning for long periods of time, over a week, and they didn't replace it. Carbon steel valves have been used at the factory, even though they were known to corrode. So, a lot of things when you add that up that you can see led to some of this accident. So, bringing this home to ammonia, this is just a link from the last month or so of just some relevant things that have come across the news of ammonia leaks in the past month or so. And the point being, I think to answer my question on the first slide, if I haven't done it yet, the reason there's so much regulation, the reason CUPAs exist and CalARP exists and all these things is because as an industry, we have too many accidents. So too many accidents still occur today. Okay, even in preparing this, I think I've probably made my point. Even preparing this talk, just some big things that have made the news recently in the last couple months. Workers evacuated, something here in our Central Valley, and then this one just this week, in Long Beach, an ammonia accident. So they're happening, almost like on a daily basis. You see something come across the news. Some of that's maybe the speed of which media travels, and definitely that's part of it. But still, as an industry, we need to do a better job of preventing this kind of stuff from occurring. Okay. There was a study done by IIAR, the International Institute of Ammonia Refrigeration. It's a little dated. It's a couple years old now. But the study was surveyed to all the members nationwide on why. Two questions were asked. Where have ammonia leaks occurred at your facility? That was the first question. And the second question is why, or what caused the accident to occur. I actually printed out, not enough for everyone in the effort to go green, but I printed out a few. If you want one afterwards, the results of the survey of the article they put together, you could come grab it. So this is a statistic from the results of that survey, which is why the accidents occurred. So they surveyed about 400 accidents that occurred nationwide and asked why did the accident happen. And you can see the results there. The predominant cause of the accidents, the biggest piece of the pie, 60% is human error. Okay? The number one cause of accident in an ammonia facility is human error. The second biggest piece is mechanical failure. Okay? And then the final remaining piece, a small sliver, is labeled as other, and in the survey said natural disasters, fire, ammonia theft, etc. So when we come to the topic of mechanical integrity, obviously mechanical failure falls into the mechanical integrity umbrella, but also human error does as well, because sometimes a mechanical failure is related to human error, right? Because, for example, when a piece of equipment may not be maintained properly, or the proper things aren't being checked on the equipment on a regular basis, which is a human error or a training type of recommendation. So interesting article, and again, you could pick up a copy if you're interested. So to answer my question, which I already did, why are there so many safety and environmental regulations? The answer is that here historically there have been huge accidents that have caused immense damage nationwide and worldwide, and that's the reason. That's the reason why we're here today. That's the reason for the safety days that happen throughout the state and the country. That's the reason for, that's part of the reason at least, and that's part of the reason for organizations like RETA, IIAR, to help promote this industry in a safe manner. So I know you guys know this, but I like to talk on the general duty clause when I give a presentation, just to remind everyone. The general duty clause states that all facilities that use hazardous chemicals in any quantity have to do it safely. Okay, because there might be the temptation, there might be some of those out there that are the less than 10,000 or maybe even the right around 500-pound facilities. Like, I don't have to do it, I'm too small. But really, you do have to do it. I just got recently done with even a US EPA Region 9 inspection of a CalARP facility. They certainly care about the way they maintain their equipment. Just because they're under the US EPA threshold, they're still US EPA is still interested in them their maintenance records, having a program that complies with recognized and generally accepted good engineering practice. So regardless of chemical inventory, it's important that the equipment's maintained in a proper manner. So what is required when it comes to mechanical integrity? I want to cover that briefly before getting into maybe the substance, just to remind ourselves, I know you guys probably mostly know this, but what does the law actually say is required, and then the practical working out of that for an ammonia refrigeration plant. Okay, so what I got here was taken out of just straight out of the CalARP regs. So mechanical integrity requirements: a facility must do inspection and testing. Okay, must do inspection and testing. Inspection of their equipment, testing of the functionality of the equipment. Okay, we're going to talk more about that. Facility must, under the mechanical integrity requirements, must train their employees. So, I mean, I guess that should make sense, but not always so much. It must, if you're expecting an employee to do the inspection and testing, train them how to do the inspection and testing. And in the previous talk that was just in this room, which Don Tragathon was doing, he was going over that, like what to train an employee on whose job is to do a daily inspection of refrigeration equipment. Very important. We run into facilities, for example, who maybe we've set up a checklist for them to use, a daily checklist to check pressures and temperatures, and they've given the responsibility of performing the checklist to the quality control manager or something for the fruit, who just is looking at a gauge and writing down the number, but the meaning of that isn't evident to them. So training is very important. Third is written procedures. So you need to have procedures on how to test and inspect the equipment. The fourth, and one that I really want to talk a lot about, is a correction of deficiency. So mechanical integrity inspections yield results of some kind. The results must be addressed. Okay? They must be addressed. That's not like optional. So facilities really need to understand that. When they hire someone to do a mechanical integrity inspection, when they bring in a consultant or a contractor, and that person does an inspection on their behalf and puts together a report on their behalf, it's as though the facility themselves is saying that they're going to do these things. And often that's a disconnect we see in the industry, where maybe they've hired someone and they think the act of doing the mechanical integrity inspection equals full compliance, where that is part of the compliance, but now the fulfilling of the action items to satisfy the full recommendations. And finally, quality assurance is mentioned, and that's one not talked a ton about. I'm going to hit on that a little bit later on. So when you look at the law, whether it's CalARP or PSM, RMP, any of those, and you look at the list of equipment covered, it's not comprehensive to our industry. CalARP lists those 6 bullet points that I have up there, that mechanical integrity applies to pressure vessels, piping, reliefs, et cetera, et cetera. And so, but you won't find anything on there like, let's say, about a liquid recirc package or a screw compressor or a ammonia adsorption tank or ammonia diffusion tank. I mean, this is a general list for all chemical processes. PSM regulation, and I know that's not the one you guys enforce, but it is a little bit different in its wording, because it says it applies to all equipment and appurtenances. That's their fancy little word to say everything. But as you'll see on the next slide, our recognized and generally accepted good engineering practice, which is requirement of mechanical integrity inspections, is in the law. So this is what can be confusing to people at times when maybe a regulator is asking for a Bulletin 109 form, for example, and someone can't find that in the law and doesn't see why is Bulletin, why do I have to do Bulletin 109? I don't see that in the law. Well, yeah, it's not in the law. It's not written in the law, but recognized and generally good engineering practice, precedent in the industry, you might say, what is normal in our industry has been stated. It's been very clearly defined, and we're gonna talk about what is recognized and generally good engineering practice for our industry. Because the perception out there, again, in private industry, I said this earlier, is that things are changing. Things are always changing. Like, it's never the same. It's always something new that you're asking me to do, and or they might say the laws are always changing. Well, you guys know the laws actually aren't always changing when it comes to CalARP. It was written in '99. I think it was updated in 2004. I think it's close to getting updated again. But it's not like it's changing every day. The law's not changing. But there is truth that recognized and generally accepted good engineering practice that does change. There are changes. There's improvements in technology. There's improvements in testing methods. There's changes maybe in personal protective equipment. Things in the industry at large do change, and that's what gives that feel. And changes for the better, I might add. So a lot of the changes that we see are for the better. They're safer, more efficient, easier. So you can look at something like 25, 30 years ago, you're not going to have computer automated refrigeration systems for the most part. Or at all. Nowadays, it's a pretty standard thing for a new design. It's going to be pretty automated, a lot of built-in safeties. That's a good thing. Everyone enjoys that and benefits from it. So it would be really strange to see a system built today that was totally operated by manual valves, for example, with no solenoid valves, let's say, and it was an operator running around opening and closing things. That would, that would be not in accordance with recognized and generally accepted good engineering practice, even though, 25 years ago, it may have been perfectly acceptable, right? So the frequency of inspections that need to be done must be based off of the manufacturer's recommendations, RAGAGEP. So RAGAGEP is our new acronym that everyone's supposed to know these days. So I resisted it for a long time. It's too long. I just tried to say it, but now it seems to be pretty kind of part of the language of the industry. So RAGAGEP, something I think we should all just kind of start using, I guess. And then prior operating experience. And that one's really important. And as a consultant, I try to implement that. You know, we start with documents when setting up maintenance or mechanical integrity programs. Start with documents such as bulletin. Yeah?
We had a release of ammonia at a facility in Roseville due to a cracked swollen valve. Now, whereas there's no requirement to replace swollen valves, what type of equipment does require periodic replacement? And can you comment on high and low pressure sides as far as
Yeah, good question. So I'll repeat the question so the camera gets it. So the question, or he was commenting that there was a leak from a cracked solenoid valve. No precedent in the industry necessarily for replacement of solenoid valves on a schedule. Comment on what components do need to be replaced on a regular schedule. High and low side. So yeah, great comment. I think the most famous component that gets replaced on a schedule that everybody pretty much knows about is our pressure relief valves, right? They're on the 5-year cycle, pretty much standard in the industry, based on manufacturer's recommendations, also based on ASME pressure vessel code that specifies a 5-year replacement for pressure relief valves. That's pretty standard. IIAR is actually doing a study. It's like in process. They commented on the results at the last conference, like developing a method for not just going based off of 5 years, but going based off of some other factors, let's say environmental and past history, kind of trying to give people more flexibility in this operating experience. But you'd have to be a really large operation, I believe, to justify the kind of testing you'd have to do even to get away from that 5-year. So regarding the solenoid valves, no, there's no recommended replacement of a solenoid valve per se, and I wouldn't recommend a replacement on a 5-year. However, solenoid valves, a solenoid valve is a component with moving parts. And just from like, hey, this would just be like machine design 101, anything with a moving part will break, right? It will break. Anything with a moving part, you can imagine I get a paper clip and you just start bending it, depending on how much, eventually it will break. So that's something we believe it will break. Now, the time that it breaks, it could be in 3 days, it could be in 3,000 years, you know, based on all sorts of factors. So that's where maintenance comes in. So solenoid valves, you said the valve cracked. The body of the valve cracked?
They did some study, metallurgy study on it. I don't know the exact outcome at this point.
Kind of interesting. Yes, Don, you have a comment on that?
Yeah, that might be related to the recall of the Sporlan brand valve that's used on compressor packages to dry the liquid for cooling. They actually put out a recall because there was a deficiency in the laser well, and these accidents were popping up across the country, and root cause came back to that valve, and the manufacturer put out a recall notice to the industry a year ago that it's the MA5 model that people need to look at. So it may have been that was the crack. There was an experience like that in Oxnard a couple of years ago too, where for no good reason suddenly that solenoid valve was making liquid from it.
So yeah, I'll just again say it for the camera. What Don pointed out, that there's a certain brand of solenoid valve that was recalled about a year ago. It's been the cause of some accidents, and that very well may be the case. Manufacturing abnormalities, even with valves that haven't been recalled. Think back to the pie chart with mechanical failures. We can't deceive ourselves. We're never going to make mechanical failures go down to 0%, right? I mean, that's not going to happen. We're not going to have 0 failures. We would like to make them less. So if we have some percent today, we'd like to lower that. But a solenoid valve, there would still be, and just further answering your question, there would be, excuse me, recommended maintenance practice on a solenoid valve, particularly in the strainer that's associated with that solenoid valve, cleaning it to prevent debris and so forth. But like a crack in the body or something, that sounds pretty significant, and not just like a valve that wasn't cleaned or something. It's more significant than that. So, and then finally, the one that I think everyone kind of knows too is that inspections should be documented. So paper trail, if it didn't get documented, it didn't happen. And there's specific documentation requirements. So MI training, mechanical integrity training is really important. And to be trained in how to do mechanical integrity well, you really need to be trained in how refrigeration works. It's hard to imagine one without the other. Maybe you could be trained on doing some real simple tasks that are real specific in regard to, let's say, greasing a bearing or changing a belt or something without a huge understanding of refrigeration. But if you're expected to be testing safeties, testing shutdown switches, changing oil and compressors, these kinds of things, your understanding of refrigeration, the cycle, is really important. And that's where I don't believe there's a better source for that than the organization of Rita. And I know it's gaining popularity with some of the Coupas locally, where I'm in locally, where they're really maybe not requiring it, but at least emphasizing it. But I think Rita certified, encouraging Rita certification, not just going through a Rita class, but actually getting certified. I'm a big fan of that. I think it says something about a basic level of understanding of a refrigeration system, the cycle, the high and the low pressures, the various components, and it will help us all speak the same language too, so that we're all coming from the same position. I understand, again, I'm talking with Don briefly after his talk, that there may be some interest in, like next year at the conference, doing like a 8-hour like Rita class for the Coupas, and I think that would be a fantastic idea and really great for you guys. I know some of you in this room have gone through the Rita class and maybe even got the certification as well, but there's 2 levels of certification. So as a Coupa, I think this gives you guys some real added clarity onto the understanding that someone would have. If they pass the Caro test, that should mean something. The Caro test is not an easy test. I'm not saying it's not rocket science, but it's not something that is just a cakewalk that anybody, even an operator, is going to sit down and ace. And the Caro test is again, it's a step above. So the Caro is for an assistant, and the Caro for the industrial refrigeration operator shows a high level of understanding, able to troubleshoot basic things. But just like a driver's license too, doesn't mean everyone's a good driver just because you have a driver's license. Same thing with Rita. It does not mean that you are absolutely free and clear of any other responsibilities. So, but it is an indicator, and something that, from my perspective and with our customers and consulting, we highly encourage. And again, luckily with our industry, with ammonia refrigeration, we really don't have like competing organizations. We have IAR and Rita, and I believe they complement each other really well in terms of what their objectives are. I see IAR more on the writing literature and doing training on the engineering side and in the standards for system design, and Rita the warehouse for all things ammonia training, and for the operator to have resources in plain everyday language that's high quality and serves them really well. So my understanding too, Rita has intention to add additional certifications for specialties and so forth, and all of that is really great. So that's when it comes to MI, if you're looking for what kind of documented training for someone that's going to be doing MI inspection, that's where I would look. Have they got Rita training? And it may be that they can be an expert without having gone through Rita, but this again would be my opinion, I guess you might say. So written procedures, is another requirement, and these can come in a variety of fashions. This is still an area that's quite often lacking out there in terms of how are the mechanical integrity inspections, the procedures for those inspections laid out. And for our company, we kind of put them together with the operating procedures. So the maintenance procedures and the operating procedures are kind of put in the same section, even of the CalART program or the RMP. It doesn't have to be that way, but there does need to be written procedures. So those written procedures need to tell an employee step by step how to perform the inspection, and that would include all the relevant information as far as operating limits, deviations they might find, steps to take if those occur, et cetera, et cetera. Okay? Deficiencies that come up during an inspection need to be addressed. So the key word in this statement here, they must be addressed. Unfortunately, still one of the most common problems that we find overall in CalARP is just past due action items. Whether it's a MI inspection or whether it's a PHA or a compliance audit, recommendation or action items just not being addressed is still a really common deficiency. And so again, this is why it's really important that a facility understand that doing the inspection is the start. That gets them up the list of what may need to get accomplished, but then completing those items is absolutely important and necessary. Yeah, comment?
Yes, just a comment. When I've seen documentation that they will be repairing deficiency, they often don't indicate when they're going to do it. They kind of leave it open. Oh yeah, maybe a month, maybe 2 years. It's depends on whatever they need to do. Amount is going to change.
Yeah, good.
The availability of the components.
Good comment. So the comment was sometimes out there you find an inspection that indicates a problem but doesn't indicate when it will be completed or when it must be completed. I hear you, and if I understand correctly, and you guys can probably correct me from the conference, that's one of the proposed changes to CalARP. Is that right? Yeah, I see heads nodding. So one of the proposed changes is giving not just, so the way it's written now, you need to make recommendations, but I guess theoretically you could say due in 100 years. Of course, we all know that's silly, but that still kind of goes on where things linger, and the next inspection comes up, well, all the same recommendations are there. Couple thoughts on that, because that's a really good point you brought up. One is, my perspective, I think we need to, again, we're private industry, so I come from that perspective too. I'm all about being sensitive to cost. And I know that's the number one thing, right? It's money. I mean, people would all drive Cadillacs, right? If we would all drive the nicest car in the world if we could afford it. So people are hesitant because these upgrades cost money. And that's where the deficiencies must be corrected. There's usually more than one way to do that. And there's maybe temporary things that can be done in the form of administrative controls, policy, while working toward an engineering control. So what I mean is, there's let's say an MI inspection. I'm just kind of thinking on the fly here. There's an MI inspection or a PHA could even be in, and there's a chance that this piece of equipment might be impacted by a forklift. Like, we could imagine that occurring. The consultant makes a recommendation. You need to protect that from being impacted. So maybe the best thing to do is to put some engineering controls, put some bollards there that it can't be impacted. But maybe in the meantime, even that day, you can create an administrative control, a sign, something painted on the ground, a policy that redirects forklift traffic in another area while something better is occurring. But the other thing I want to say about this too is that when a recommendation is made, it should have a timeline on it. So, yes. Yeah, so the PHA has to have a due date. And I say the same on any, I believe that on any recommendation. I don't care if we're even talking CalARP or not. Like if you're going to recommend something and you're telling them you have to do it, we will all work on time schedule. We need to know when we need to do it by. So go ahead, Baronia.
Proposed changes is will include the mechanical recommendation, the PHA incident
Investigation.
investigation, and the rear.
Compliance audit.
So they're going to put a time limit on it, but still is going to be, it's not 1 year anymore, they took that one. They're thinking of a year and a half, maybe 2 years. But still it's going to be upon the CUPA to see the risk involved, and like you mentioned, the cost.
Right.
I had a facility who they needed a lot of equipment and was costing more than $250,000. So we started with the priorities first for the risk and then go from there. So it's up to the CUPA to follow up on the recommendation if they're addressed or not.
Yeah, so just to repeat what Baronia said, so it's on the camera, the proposed CalARP change is to mandate some time limit, and that's still up in the air, whether it's going to be a year and a half or something in that realm, for PHA recommendations, MI recommendations, compliance audit, and incident investigation recommendations to put a time limit, but it's still up to the CUPA and the facility, hopefully the private industry sees serious things as serious, to evaluate the risk. And there are certain things that need to be addressed. There may be the case where something does need to be addressed tomorrow, or the equipment is not safe for further use. It cannot wait a year and a half to be remedied or fixed, right? So that was a good comment. So, okay. So common deficiencies, this is maybe the little section that overlaps with some of the other talks, but things that are just common that you find out there that pretty much every system that's more than a few years old will have to one extent or another, to one degree or another. This is a picture of just various forms of corrosion. So often in ammonia systems, they're made out of carbon steel. They're connected with carbon steel pipe. And again, carbon steel pipe corrodes. It's not a matter of is it corroding? It is corroding. What rate is it corroding at? If it's kept clean and painted, it will be a very slow process and it will last for a very long time. If it's totally untreated and left to the elements and it's subject to wind, rain, dirt, and all the rest, it will have and sulfur dioxide gas, if you're in the table grape industry, it will have a very short life. Very short. So this is a common thing we find out in doing MI inspections. This picture here on the right side is of particular concern where the pencil, it's a little hard to see on yours, but the pencil is showing a pit, which versus maybe what we typically think of when you think of kind of the orange color on carbon steel pipe of corrosion, we maybe refer to as uniform corrosion, where you have material loss spread out fairly evenly on a surface. But a pit is actually more significant or more severe from our perspective, because pitting corrosion is likely where the hole is going to develop. From the localized pit, and a pit is a form of corrosion where it's local material loss leading to an eventual pinhole leak. So in fact, just working with a customer, just before I walked in here on a phone call with them that has coils that are corroded, and they want their coils tested. They want them tested with like ultrasonic to determine the wall thickness. Discouraging that, or saying I don't think that's going to be that beneficial to you. And the reason is because the problem in that case, because I've seen them, is the pitting. And technologies, even like ultrasonic thickness, which can tell you the wall thickness, on uniform corrosion aren't going to be that effective on a pit, because you're not going to get the smallest, you're not going to get the head inside the pit to measure the depth of that, if that makes sense. So these are common deficiencies. Yes?
Question on looking at corrosion. If you have a lot of insulation on pipes, what does the IIAR say for frequency of looking at the insulated pipe for corrosion under insulation?
So the IAR,
What's RAGAGAP?
yeah, I can tell you what I say, and it's based off of IAR. What we tell our customers, when it comes to insulated pipe and doing mechanical integrity inspections, we recommend doing a thorough visual inspection of all pipes. So before you ever get into measuring wall thicknesses, pits, ultrasonic testing, x-ray, whatever it may be, a thorough visual inspection. They use your eyeballs. They're very valuable tools. They work really good, and look at everything. So when it comes to insulation, where you can't see the pipe and all you can see is the insulated surface, hopefully the jacketing. So ammonia insulated pipe should be jacketed, probably either with PVC jacketing or aluminum jacketing. You're looking at the condition of that, and you're looking for things like moisture on the outside or ice buildup on the outside. If you're seeing moisture and ice buildup on the exterior of the insulated surface, it's an indicator of what's going on inside or the condition of the insulation. Now, in really, really humid environments, you will still get that. You will still get it. And so I'm not saying that it means that the pipes are horrible or anything. But if you got tons of ice buildup outside the insulation, probably your vapor barrier shot, and the insulation's in bad case, I would guess you're going to have some corrosion going on. So to answer your question, Michael, our recommendation is when insulation looks right, when it looks like it's in good shape, when it's the joints are sealed, the jacketing's in good shape, all signs indicate it's fine, we don't recommend cutting into it, because then you've cut into it. And you've just broken the vapor, you've made a break in the vapor barrier that you're going to have to reseal up. And so forth. But if you see areas that are in bad shape, then that's where we recommend, all right, it's already in bad shape. You need to repair it. We're going to make that recommendation. Let's cut a section off that'll be nice and clean where you can repair it, and let's test that area. That's our approach, our thinking on the subject. Now, I've seen people that cut like coupons in the insulation with plugs, and that's pretty cool idea. I think it's a neat idea where they basically cut squares or circles that can be removed. They can do their testing every 5 years or as often as they have specified in their program, and then they put those back. Again, my concern in that long term is I wonder if that's a source of infiltration into the pipe and damaging further equipment. But they can't just not care about it because it's insulated. Or say, well, I can't inspect it because it's insulated. Then inspection of the pipe insulation goes a long ways. So other common deficiencies, you probably see a problem here in this one of these pictures, or both of them. But trees shouldn't grow on top of evap condensers, right? That's not a garden. That's one problem. Second problem, and it's, again, maybe lighting's a little hard to see, but you see something, a hose dragged up there and a little, kind of like a sprinkler deal you might put on your lawn. Probably not the way BAC or Evapco designed the thing, you know. There's some indicators like that thing maintenance hasn't been done on that in a while. I don't think it's had an MI inspection in a while, because how long does it take for a weed to grow, 18 inches tall? A little while, because you got to get enough dirt and muck on top of the mist eliminators for the weed to have some amount of root to grow up. So crud on the side, leakage from the condenser, an indicator of issues with their water treatment, the integrity of the wall of the condenser, etc. So the evap condenser, when it comes to prior operating experience, when we talk about cleaning an evap condenser, prior operating experience is huge, because I think Bulletin 110 for IAR Bulletin 110 says, I think, don't quote me on this, but I think it says every month to clean it. Something like that. For a lot of facilities, that's pretty overkill. In my opinion, it's not necessary, but prior operating experience will clearly tell you how often it should be cleaned. If you're in a really dusty, dirty agricultural environment, which a lot of facilities we work with are, the condenser could be renamed air filter. because it pulls that dirty air through water, which washes all the dirt out, and you got super clean air come out the top, and then the dirt sits in the bottom, right? And that's why it gets all mucky and dirty. But if you're in an urban environment and it's mostly city, not a ton of dust, the amount of crud that will build up in the bottom will be less. It will be very site specific, is what I'm trying to say. And so operating experience is real valuable when it comes to evap condensers. Okay, pressure relief valves, common deficiency still. It's getting a lot better because most Coupas are, enforcing the 5-year replacement, and so that's getting a lot better, but this wasn't taken too long ago. Well, Michael, this is kind of a good example. So if we come across this kind of stuff, let's test it. This is obviously in bad condition on the insulation side. On the relief valve side, those are old relief valves. They're not vented properly, of course. There's all kinds of problems going on. Here's another picture here. Problem, right? It's a relief valve that has a nipple coming on the outlet, a 90 pointed down, another nipple, then a cap. So it's got some little cute piping ultimately capping the relief valve. So how does a capped relief valve work? It doesn't. To answer the question, it doesn't work. So this would be an example of when should this get fixed? Like now, yeah, like there's nothing protecting that piece of equipment. So if it was designed into the equipment as a safety device, the safety device is gone. You think, it's like the example of Bhopal shutting off the safety system to save energy. They plugged these probably, I'm just guessing, I don't know why they plugged them, but probably because they lifted and then they didn't fully reseat and it was seeping ammonia out. And it was bugging them. They wanted it to stop, and one way to stop it was to put a plug in it. Okay, that would be something to look at as a real significant violation that should be corrected ASAP. So relief valves are still an issue, and now even that relief valves are getting sized or are getting replaced pretty regularly. One thing we run into quite frequently is still the discharge piping. Being appropriate. So relief valves that are discharging like right at eye level or even lower than that. Relief valves discharging inside of buildings, for example. Inside buildings of, let's say I was at a facility that had a liquid recirc package with a little oil pot, and the oil pot or the recirc package was vented properly, but the little oil pot had a relief valve. Well, it was just right there inside the processing areas. Like if that relief lifts, it's going to expose hundreds of people unnecessarily to ammonia that don't need to be exposed. Okay? Other common things we find out there in MI inspections that come up, and they become a kind of a area commonly with our customers of like confusion and frustration, I might say, is in regard to, that's showing a ventilation fan. I just picked one off the internet, but an engine room ventilation, secondly, an ammonia detector, and those two are common areas of frustration because current code requirements specify how engine rooms need to be ventilated for continuous exhaust, for the emergency purge in the case of a leak. But people often say correctly, well, this place was built 30 years ago. That wasn't required then. I built it according to the codes at that time. And that's accurate. I will agree with that. So when a code changes, and they're usually on 3-year cycles, codes change on 3-year cycles, it is not required that every facility upgrade every single thing they have to meet the new code. That'd be enormously expensive and not a requirement. However, some of these things, so the basis of requiring them is not because it's in the code. The basis of requiring it from an MI inspection or a health and safety inspection is because it's a health and safety concern for employees or the public at large. So that would be the reasoning, if that makes sense. So that comes up quite frequently where we reference something. Now, when they go to install one, if it's been recommended, let's say an engine room, a machinery room that has no ventilation or very inadequate ventilation, and we recommend to install a ventilation fan, well, we're going to recommend to install according to code, right? So they're not installing it because it's in the code per se, but if you're going to go through the process of upgrading and doing it safely, do it according to the code, if that makes sense. So ammonia detection is one. I mean, there's still a lot of facilities out there that don't have ammonia detection, either stationary or even portable detection, meaning handheld detectors or worn detectors. And I know it's not a CalARP. This thing I'm about to say is not a CalARP issue, but you cannot satisfy Cal-OSHA in terms of making sure your employees are not subject above PELs without some kind of detection. So Cal-OSHA's PEL for ammonia is 25 ppm. You really have no way to demonstrate that if you're not measuring it in some fashion. So I really think ammonia detection at this day and age is something that facilities should have to one extent or another. Now there are issues with ammonia detection that I'll talk a little bit about. Again, I mentioned this, but one of the industries we work a lot in is the table grape industry. Where we are, there's a lot of table grape cold storages that utilize sulfur dioxide gas for fumigating their grapes. So inside an ammonia warehouse, they inject sulfur dioxide gas, which is another CalARP chemical. But so you got a combo thing going on. Well, it just so happens sulfur dioxide gas pretty much destroys everything. Pretty much destroys everything. Nothing, especially at these high concentrations. So it'd be all great and everything to put one of these inside the room, but it'll get ruined. It'll be done after a month. And unfortunately, there's not a technology that I'm aware of to remedy that. So what that means is that you can't really monitor the ammonia in the room while it's being gassed. So what's common in our area at least, and maybe even across the country to some extent, is what we call sample systems, where you draw air from the room to a common sensor through tubes using a vacuum, and you're pulling air and they maybe call them sniffers or something. You're pulling air from the rooms. And then when the room's being gassed, we shut that off because we don't want to pull sulfur dioxide gas. But then we're not monitoring ammonia anymore. But that being said, there won't be any employees in the room while it's being gassed, right? They can't be because they wouldn't be able to live in that environment. So, there has to be like reasonable approaches to some of the problems faced there by industry. And I know that's one example. So another common deficiency in what's shown here on the right-hand side is that an e-stop, one form of an e-stop, a break glass switch. This one, you guys have seen them, I'm sure. Got the little hammer hanging next to it. And what you do is you break the little glass here, which releases the switch and will shut down. Generally, it shuts off the engine room compressors in the event of a high side emergency. So often these are installed but have never been used or tested. So that should be part of a mechanical integrity program, is testing the e-stop, that it functions, that it's present and functions. Okay. So quality assurance, this is the kind of just interesting, like maybe one of the more oddball parts of MI, isn't talked about a lot, but quality assurance is stated in the CalARP reg that new equipment must be suitable for the application. Don't see a big problem with this. I haven't found too many places that are like trying to design their own custom heat exchangers or something like that. I'm sure it happens. A couple come to mind, actually, that have done some of that stuff. But generally speaking, you're buying from legitimate, reputable manufacturers, the Fricks, the Vilters, the Mycoms, Colmac Coil, and there's a number of Evapco, BAC, a number of manufacturers that are well known that have literature that's supported or involved in the industry, and not a big issue. One thing that does come up, though, occasionally, particularly on piping, and sometimes, unfortunately, on other areas of the piping, is components being used in a refrigeration system that are not that have a brass or a copper associated with them. And as we need to know or emphasize, ammonia is really corrosive to any copper and copper alloys, brass, bronze, etc. We see it a lot on relief piping, especially the unions on relief piping that have a small brass component, and it gives you an indicator actually that one's lifted, because it turns that greenish color, and it gives you a helpful clue that a relief valve has lifted. But in the ammonia system, that's one thing to look for. Another one is on the tanks, on the diffusion tanks for the facilities that have water tanks. Brass and bronze is great in water systems. But on the diffusion tank, you don't really want a brass or bronze valve at the bottom. If it's fresh water, it'll be fine. But as soon as it has a release into it, you're going to start a corrosion problem on the valve, which will develop a leak on the ammonia diffusion tank or ammonia adsorption tank. Okay? So existing equipment must be properly installed. That's another of the quality assurance requirement. And finally, maintenance materials and PPE must be suitable for the application. So this is one that we, for a facility that does their own maintenance, that should be evaluated as well during an MI inspection to make sure that their personal protective equipment. One thing to maybe to start asking in some of these places is to see their ammonia hose that they use. Or maybe don't even ask it that way. Maybe ask to see that what do they use? Do they use a hose to drain oil, for example? Because we have seen some scary things from using a garden hose, air compressor hoses, various kinds of hoses in an ammonia for maintenance type purposes, for draining and purging. So that's an area. In fact, there was just a story today as far as a hose that had broke and the final kind of settlement in regard to that. So hoses can break, and there's a specific rating for ammonia hoses that should be used. If a hose is kinked and been driven over and stuff, it needs to be replaced. It's not safe anymore. Another thing I want to point out in this quality assurance area is that there's other components that are not directly part of the ammonia system that are really important to be maintained or be aware of. One that comes to mind is for compressors that are water cooled, recip compressors and some screw compressors as well. There's a jacket water pump. You're talking a small pump. It may be 1 horsepower, it might be 3, 5. It's not going to be anything substantial. But that pump, if it fails, if there's only one of them, will cause the compressors to overheat and not be able to run. And so it's just a good thing for a facility to either have a backup of those pumps, or at least have availability, replacement quickly, and to know about that. So anytime there's one component that will cause a big failure of a system, we consider that a critical component, even if it's a 1 horsepower pump that you could buy off of Granger. It's in the facility best interest to even have a backup available. So. Oh, and that's, I guess I jumped ahead. So that would be like maybe what a jacket water pump might look like. Just a typical centrifugal pump, nothing extraordinary. So looking at quality assurance, so this would be the personal protective equipment, like a handheld monitor. It should be appropriate for use, meaning it should be calibrated. There should be records showing that. For new equipment, it should be appropriate. Typically, like screw compressors will state that they're designed for R717. R717 is ammonia, the designation for ammonia from a thermodynamic perspective, and look for that. We occasionally find a compressor in an ammonia system that says R22. R22 is a freon refrigerant, and usually that just causes us to look further into it, and it's undergone some sort of retrofit, and it's fine. But still, it makes us question the situation. One story I'll share briefly that we ran into, because we were talking about brass and bronze. When compressors are shipped, they're charged They're charged up to some pressure with nitrogen and fitted with a gauge on the oil separator. So this is a screw compressor, a brand new screw compressor. That's why it's still wrapped in plastic and stuff. And they're shipped and they have some nitrogen charge under pressure with a gauge. Well, the gauge they send is a little cheapo gauge. It's not like an ammonia gauge. It's a little gauge that is has some copper in it anyways. And we had a situation where we installed it and that little thing wasn't caught. And we hadn't even started up the compressor yet, but we had introduced a little bit of ammonia gas to check rotation or something. I'm not even sure all the details of it, but it had been installed, hadn't been started up yet, and there was some ammonia gas in it. Well, anyways, over the night, just over that night, the threads corroded and it began a small ammonia leak. Just like that. It wasn't a significant thing, but just something like that, to be aware of that kind of stuff. I wish, in that case, the manufacturer wouldn't send it with that, but part of the startup procedure is to remove that gauge and either replace it with an appropriate gauge or whatnot. It's just there for the shipment to show that it's charged up. Okay? Oil is another thing. Okay? Quality assurance on existing equipment, oil management. The mixing of oils can cause huge problems. Start mixing various oils with various properties, or you get someone that's a car mechanic background and just confident that he could rebuild anything and puts automotive oil in or something screwy. You could be facing some big problems with your system that can lead to a system failure. So knowing what kind of oil your system has, what kind it uses is important, and that it's maintained consistently. Okay? So Ragaget. What are sources of Ragaget? As Koopas, I hope you guys have access to some of these things I'm going to show here. I printed out several Bulletin 109 forms. I don't know if you guys have access to them or not, but IAR, I actually requested permission, and they were fine with it, that we print them out. So if you want to take them, you can, just for reference as an example of a standard form. But I'm going to walk through here some examples of what's considered RAGAGEP, recognized and generally accepted good engineering practice. The predominant RAGAGEP in our industry for mechanical integrity are these two historically. Have been these two documents, IAR Bulletin number 109 and Bulletin number 110. So IAR, a long time ago, wrote a series of bulletins ranging from 106, I think, up to 114 or 16, I don't know. They wrote several bulletins, about 10 of them probably, on various topics. These two happen to deal with the topic of maintenance and or inspection. Okay, when I asked, and that is where these inspection forms that probably some of you have seen because they got turned into you as part of the CalR program came from. So they're in the back of Bulletin number 109. It's a great document. However, IAR gave me one contingency upon sharing these with you, which was to emphasize that I tell you that IAR's plan is to do away with Bulletin number 109 and 110. These documents are going by the wayside. So Bulletin 109 and 110, which are up here, this is what they look like. The forms at the back are two-sided. The front usually has the equipment info. The back has the checklist of what to do. Okay? But IAR is removing all of their bulletins. Okay? They're getting rid of every single one of them and replacing them with 8 new documents that they're calling standards. Okay, and this kind of sounds like just semantics, legalese, and it kind of is, but essentially, in a nutshell, what's happened is that the bulletins became treated like standards, like codes, which wasn't really the intention of IAR. When they wrote the bulletins, whenever those were written, they were written as a guideline, as a help to the industry, and instead it kind of got taken in a sense, and the industry got bashed with their own little supposedly helpful tool. So IAR is redoing their documents and writing these 8 standards, which are going to be written in code language. Okay? So they're writing now with the idea that, okay, what we put down is RAGAGEP. And each one of these standards is going to have 2 sections. it has a normative section and an informative section. So all kinds of new vocabulary, but normative being required, you might say, required, everyone should do this. Informative being optional, or here's an example, and so forth. Hopefully that makes sense. So you see all the various colors here. This is the stages of where they are in this process, which is going to be really important to you guys as Koopas. 1, 2, and 3 are done. They're published. They're published documents in practice. So IAR 1 is definitions. Easy. So IAR 1 just is kind of the table of contents, you might say. So it's just defining terms so that everyone's using the same language. Okay? IAR 2 is a document that's been around since the 90s, actually, and it's for equipment design. Originally, it was called equipment design and installation, but as you can see, IAR 4 is going to be installation, so they're kind of breaking it up. So this document is going to govern the design of equipment, so design of compressors, design of pressure vessels, design of condensers, etc. What needs to be on the nameplate, those kind of things, okay? And this is, again, it's already been distributed, already in production, already for sale. You can buy it off the website and so forth. IAR 3 is all about valves, valve design, okay? And that, again, is already in production. It's already been released, okay? Number 4, okay, let me skip 4 for a second. 5 and 7, the red ones, they are in public review right now. So these two documents have been released but are not final. So the way that ANSI certification happens, it's kind of a long process. So the committee writes the standard, they put it out to the public reviews, comments, and it goes through this process, and it can take a while. So I've participated in the review of both these. Like, I provide comments because I know it's going to affect me, our customers, our company, and so any feedback is welcomed and helpful. So these two will be the next two released. You can see one of them is about operating procedures. That will, that will obviously impact the Koopas, you guys, to some extent. Startup and commissioning. So this will be an interesting guideline now that will affect MOC, PSSR in CalARP. So it'll give us a clear idea of what the industry should be doing by and large on starting up a new system or a new component. Installation is being written right now. Okay. So, and I'm not on the committee, but a corresponding member of this kind of committee here. And basically, we're starting with 2 and removing all the components of install. And this will specify how to put together a system, how to pressure test a system before starting it, and that sort of thing. So that's what installation is all about. And then 6 and 8 have, to my knowledge, have not been significantly started yet. And they may have outlines and so forth, but the green ones are still going to be coming. And they cover 2 topics, which is maintenance and then finally decommissioning. Okay? So they're calling this the suite of standards. And these 8 standards are replacing all the old bulletins. Okay? So Bulletin 109, Bulletin 110 going away. Yeah, question? So the question was, who's reviewed them? What agencies have reviewed them? I don't know the answer. So the public review is a public review. So like you can go to IIAR.org and like review yourself if you want, 5 and 7. Send in your comments. Now, IAR does have a close alliance with OSHA at a federal level. And I'm only guessing, but I think that there's probably been communication in that regard on that level, but I really don't have the facts on that to what extent. Yeah, do you have something there, Don?
They have collaborated. Before the standard was put out for peer review, it went to Jim Lay and the PSM group at Fed OSHA for their review and comment. Comment coming back is whatever you put there, we're going to enforce. So, but yeah, there is an alliance and a line of communication between industry and
Yeah, good. So Dawn just agreed that there is an alliance between OSHA and IIAR and some communication going on. When I review them, when I'm doing like a public review, like from my perspective, I mostly looking at it like what Dawn just said, like what's here is going to be enforced, and trying to remove, like say, well, maybe this shouldn't be enforced in all cases, so it shouldn't be there. That's usually kind of the perspective. Okay. So yes.
And related to that, so if IIAR was displeased, so to speak, with the agency sort of grabbing a hold and requiring certain things or identified in the bulletins, are they having these two different columns, the normative and informative columns, to remove some of that stuff over the informative area?
Yes.
So that agencies cannot directly enforce that? Is that part of the plan?
Yeah. Yeah, so the question is, if IAR was frustrated with Bulletin 109 and 110 being used from a regulatory standpoint, is that why they're making it normative and informative so that regulatory agencies can't enforce it? I don't think IAR, I think IAR knows they can't stop anyone from enforcing anything. That's one of the things I'm going to be interested to see how it works out, how the informative section will be treated. But I think, Michael, their main point is they're just now trying to be more careful with their language, knowing that what they write will be treated as a standard, as a code, basically. It'll be forced upon people, and so it's being written from that perspective. These aren't so when it comes to like the design, installation, let's say, when you talk about installing an ammonia system, if you need to learn everything you need to know about it, you're talking about a 500-page textbook probably or more. If you're talking load calcs and all this, that's not what this is. These are bare bones documents covering what they feel should be treated as, okay, everybody needs to do this. The rest of it needs to be done by an engineer, and so forth. Yes?
Do the owners of the refrigeration companies of ammonia have to purchase this thing?
So when the question is, do people have to purchase these? And the answer is, of course they do. So yeah. So the books always cost money. But membership, actually with IAR, if you are a member, these can be downloaded for free as PDFs. But membership costs money. So everything costs money. Yeah, Don.
Yeah, just comment back to the normative and the informative. What I appreciate about it is if it's normative, in the discussion, do it. The informative, what I've read from that is, here's a good technique you might consider. And that could be considered maybe, from your perspective, should you be doing this. But normative, hey, we're talking about it. This is what we're going to do. So that's why I appreciate that they are saying those out in code language. And they will be code because the way that the codes are being written now, it's all by reference to a standard.
Yeah.
So it has to be done right.
Right, and they're working hard, and these are coming up in a future slide, but I'll talk about now. They're working hard to coordinate with ASHRAE, because ASHRAE has a standard, ASHRAE 15, and with the model codes, which are on a slides coming up, more ragged again, but they're working hard to not have, someone have to look at 15 different things to figure out what do I need to do here. It's going to be hard to do, though. Yes?
Can I ask about the propane, not propane, but ammonia tanks? I assume they're listed or certified in some way, some body oversees approval of how tanks are constructed to hold ammonia. Is that separate from another separate entity from your industry? Secondly, are there unique things in the ammonia industry such as threads? In the medical gas industry, they have certain kinds of threads designed so that they can't marry together with other gases. Can you comment on those two?
Yes. I'll answer your second one first, and the answer is no on the threads. So it's a standard pipe thread on ammonia system. Typically, I haven't seen any backwards or unique threads in general. So that's the easier one to answer. As far as the governing body on pressure vessels, pressure vessel in an ammonia system needs to be in accordance with ASME Boiler and Pressure Vessel Code, Section 8. So that would be the governing body. That being said, the ammonia pressure vessels are not permitted in the same way that, let's say, air compressors and boilers are. They're not permitted in that fashion. So, but so to be a certified pressure vessel manufacturer, you have to go through a rigorous protocols to satisfy that. And ammonia, what you're looking for as an inspector is the nameplate, and you're looking for the little clover, the little clover, which is the ASME clover punched on it. Usually it has a U inside that clover, which tells you an unfired pressure vessel. When unfired means it's not a boiler, it's not got flames under it in any way. So interesting topic, since it came up, is what to do with the vessel that doesn't have a nameplate because it's so old or something, or corroded off or whatever. And unfortunately, I think EPA has been pretty clear on the topic. Means if you don't have a nameplate, you're kind of up a creek. You need to get a nameplate, meaning go through some sort of vessel certification process. And there's not really good news if you don't have a nameplate that I can see, unfortunately. There's things you can do, like if you're concerned, you can do testing. You can do ultrasonic testing. So if you know it's carbon steel, you can test it and determine a thickness. But in the absence of the original design specs, the original thicknesses and so forth, it's still kind of an estimation. So I don't know what else to say about that one. So other RAGA-GEP. RITA is a source of RAGA-GEP. We talked about RITA in terms of training, but RITA has some recognized and generally accepted practices when it comes to daily inspections, daily logs. In fact, Don passed out information in his talk about doing daily rounds. That's RAGA-GEP. When it comes from an organization like RITA, it's considered RAGA-GEP. Okay. I mentioned ASHRAE 15. This is another pertinent standard referred to frequently. And then the uniform codes. Okay, this is a really confusing mess, but you might run into it somewhat. So there's different codes that apply to different jurisdictions, and they're different from each other. So kind of in the way that CalARP, RMP, CalPSM, FedPSM are all about the same mostly, but kind of different, you know. It's kind of the same in terms of when it comes to model codes. But there's two main groups, which is the uniform codes and then the international codes. Most of the country uses international codes, but California is in the uniform code. So California is actually in the minority, and some other western states still working off the uniform code, and California kind of even takes that and tinkers a little bit with their own model code called the California Mechanical Code. So Chapter 11 of the California Mechanical Code will specify all sorts of information about how a refrigeration system must be designed. It would be a good thing to have a copy of as a regulator, I'd imagine, if you could. Yeah. Oh, no, you pay for it. Yeah, so yeah, all this. These organizations, hey, it's like college textbooks. You know, they update them every 3 years. You got to buy them new, man. It's frustrating. They're not cheap either. So yeah, every 3 years are in a cycle. But these organizations here that write them, yeah, they probably cost, I don't know, $150. Something like, I'm just guessing. I haven't bought it in a while, but more RAGA-GEP. This is kind of the modern thing, especially for maybe the younger ones of us that like technology, but there's forums, industry groups that are really active. And while this is, just because it's on the internet does not make it true. don't go that far, but you can find answers to questions on the internet. And I mentioned here an industry forum, a pretty popular one on LinkedIn, kind of run by the Garden City guys that run the school out there, but it's got input from all sorts of sources. You can see here Eric Smith, he's one of the IAR employees, and as a regulator, I think it'd be a cool tool for you, because you can go, someone's asking about a question about a solenoid valve getting stuck or this or that, and you might have 20 different responses from all around the country. It's quite fascinating what technology allows us to do now. So that's really becoming another kind of realm of RAGAGEP. So let's check our time here. Yeah, our time's quickly passing by. So I think we've talked about a lot of this stuff here. I was going to give some examples, but we've covered them in terms of our just throughout the talk. So the last thing I wanted to cover today, and this is kind of just in closing, is to talk about some of new developments, maybe you might say, new studies in operation and maintenance for the larger organization, private industry that are doing studies. There's been considerable money invested to figure out what is the best way to do maintenance. Okay, and this is a Department of Energy study. This you can get for free, though, so you can go download it. I also brought a few copies about operation and maintenance best practices. And it kind of is going at some of the old school thinking about operation and maintenance. And the good news is what they're proposing lines up with mechanical integrity requirements, and the study shows it will save an end user considerable money. So I'll cover it briefly. So we know this is called a bathtub curve. We learn in failure of things with moving parts that everything fails, and typically failure rate here on the vertical axis is. And then this would be time on the horizontal axis. Failure is more likely in the infant stages because of equipment problems or manufacturing error, and then of course at the end of its life. So everything goes through this period where it has an infant mortality, a useful life period, hopefully that's a long time for us, and a wear out period. Okay? And we look at it from a regulatory perspective, kind of thinking with our prevention program elements. This is our PSSR, right? Pre-startup safety review. When you start up equipment, make sure it's designed right and installed right and functioning. Once it's working, we move to an MI kind of phase, just maintaining it and testing it. And then finally, it's going to start wearing out eventually, and you're going to do an MOC, right? So the study, what it outlines is 4 different types of maintenance programs called reactive maintenance, preventive maintenance, predictive maintenance, and reliability-centered maintenance, okay? And I'm going to touch briefly on each of those. I think we all know what reactive maintenance is. Reactive maintenance is not doing maintenance. Reactive maintenance is when something breaks, we fix it. And still common, still used too often, okay? The study showed it's the predominant mode of maintenance. 55% of all maintenance is reactive. People fix things when they're broken. Pros and cons. Reactive maintenance, what people will say the pro is, well, there's no line item in their budget for it because they're not doing it, right? So it pencils out nicely from that standpoint before the season. And then less staff requirements because you don't have to have someone doing maintenance. But the cons are pretty evident. Unplanned downtime, overtime work because something's going to break in the middle of the night, more expensive repairs, inefficient use of your staff. Okay, I think we all see why it's not a good, I even think most private industry sees why it's not a good or the best option. Preventive maintenance is a very common term. We're all familiar with it, and maybe even speak well of it, but it's really an idea developed by the military, the U.S. military, where we do things on schedules based on time, okay? And when you look at it from the military perspective, where they've got a lot of people, and really with a lot of time, right? A lot of people on an aircraft carrier at a time when it's not a war are drilling, right? That's what they do. They do drills and they maintain equipment and they make sure they're ready to go. And so preventive maintenance makes a lot of sense. However, when you look at some of the, and before I go to that, the study showed a 12 to 18% savings over reactive. So preventive is better than reactive. But some of the cons is that it's labor intensive and you may be doing things that you otherwise don't need to be doing, right? You may be doing it every year when it could be done every 2 years and you could be saving money, okay? So that's preventive maintenance. I know I'm going a little quickly just because time's running out. So predictive maintenance, which might be a new term to some of you, is one that's really growing in our industry. And as Koopas, I think you should be familiar with it. And that is, instead of doing just preventive maintenance, like on a regular yearly schedule or monthly schedule, Predictive maintenance is where we begin to use technology, we begin to use training, we begin to use our understanding to better pinpoint when maintenance needs to occur. Okay? And so the classic example on an ammonia refrigeration system is on a screw compressor, that's very common, I'll add, is doing an oil analysis on a screw compressor. We don't just change the oil every year. It's too much oil. It costs a lot of money. So we pull a sample, we test the oil. If it's bad, we change the oil. If it's good, we continue to run it. So the predictive maintenance, the testing of it is the predictive part. Vibration analysis is another form of predictive maintenance. We don't just replace the bearings on a screw compressor just because 5 years have gone by. But what we would recommend maybe is they do vibration analysis on a regular basis so they can trend the condition of those bearings and pinpoint, okay, the bearing failure is going to start occurring around this time. Ultrasonic thickness testing. We don't replace pipes just because they've been in service 20 years. A pipe that's been in service 20 years might be in horrible condition, but it might be in great condition. Right? I mean, it could be either way, but doing ultrasonic testing on the pipe gives us an idea, more information, right? So predictive maintenance might be kind of this is, I believe, the direction I'd like to see the industry go in adopting more predictive tools. Now, what does predictive maintenance require? What are the cons, you might say? There is an investment. The investment is in the diagnostic equipment. So to do ultrasonic testing, do vibration analysis, it costs money to get that equipment, to do the training. You might have to have a higher skill level of personnel that's able to do that. These are all challenges to predictive maintenance. And it might be hard to convince somebody of the savings. Vibration analysis, for those that aren't doing it now, aren't familiar, it's a difficult sale still sometimes. People sometimes like, okay, I hear a weird noise, now I want to do vibration analysis. That's actually kind of reactive, right? You see what I'm saying? That's kind of a reactive maintenance. Predictive maintenance will say we're going to do it before we hear the noise so that we can determine the condition and begin trending that, okay? And so then what the article and this study eventually so here's a brief example, but we're kind of running low on time, so I'm going to skip that. So what the holistic approach that the article or the study is promoting is what's called reliability-centered maintenance. Believe it or not, just today you might be seeing this as job titles more often. I was at a facility where they've been working with the maintenance manager, and his job title changed. His job title is no longer maintenance manager; it's reliability manager. So it was interesting as I was going into this talk, even seeing that, but that's what they're promoting in the study is what they call reliability-centered maintenance, which says that not all maintenance should be treated the same way. That we want to use the technology that we have, the understanding that we have, the criticality of the component, and decide based on that. So there are certain types of components where reactive maintenance may still be fine. I think of a component, that for whatever reason is inaccessible or uncritical. It may still be fine to let it go until it breaks because it's not going to harm anything and it's easy to fix. But there may be other things. Let's say greasing a bearing that should just be done on a preventive maintenance schedule. Just do it every year because it's easy to do. No sense in testing the grease in the bearings for, let's say, a fan because that's overkill. But some combination that combines reactive, preventive, and predictive to form a really solid maintenance or mechanical integrity schedule that meets the needs of that facility. Okay, I promote this. I think we face challenges because, again, it's hard to convince people. It's hard to convince people, but the study showed this, and this is across the board in their study that is Department of Energy, that reactive maintenance, the annual cost per horsepower per year, so that's what this number is $18 per horsepower per year. It'll cost you if you go fully reactive, no planned maintenance. If you do a preventative program, it's going to be $12, $13 per horsepower per year. So you got a considerable savings there. If you go predictive predominantly, you'll be down to the $9 per horsepower per year. And then finally, you combine these in a way that best suits you, and you can really see your best savings. So anyways, really interesting to me, and I have the article up here, but you can download that as well in the Department of Energy study. So here are some examples when it comes to reliability-centered maintenance in ammonia systems, particular areas to emphasize. We talked about vibration analysis, ultrasonic thickness testing of pipe and vessels to start trending where we are in the cycle. Oil analysis on screw compressors. See, I think you even maybe look at a screw compressor and a recip compressor differently because of the quantities of oil. And a recip, it may still make sense to just do it every year because the cost is so low. Okay? Ammonia detection, as far as calibration, you need to follow manufacturer's recommendations, but maybe some combination of calibrating it annually, but also doing like a bump test periodically just to see if it functions in some way. Relief valve, discharge pipe, oil draining, and then finally compressor maintenance, which ties back to vibration analysis. Each one of these, so oil draining, I'll say just quickly about that. You might have it based in your maintenance program that you're going to drain oil every year, but really, if you go to that oil draining station and it has 100 gallons of oil in there, you should probably be draining it more often than that, or fixing whatever's causing that much oil to get in there. But you get what I'm saying. But based off of your operating experience, you're going to be pinpointing and dialing in your maintenance or mechanical integrity program. Okay? So I know my time is just about up. So, and that's my last slide. So I appreciate your guys' time. Hope that benefited you guys in some way. And if you have any questions, I'd be happy to try to answer them. But I know we only have a couple more minutes for I think there's one more talk in here that we'll start. So if you wanted the handouts, I printed a few, not enough probably for everybody, but feel free to take them. And again, just thank you.